Okay, so now we've developed kind of the background for looking at limits of trig functions. We have the squeeze theorem, and we also have the two identity for limits. So let's start with something involving the squeeze theorem. So these are going to be examples. Let's say I want to find the limit as x approaches 0 of x squared times sine of 1 over x. We want to know, what is this limit? So the first question to ask is, can I just plug in 0? Well, let's see. If I plug in 0, I'm going to be dividing by 0, so I definitely can't do that. So I definitely can't divide by 0, so I got to do something else. Let's try to squeeze this function between two other functions that have the same limit. So let's start with one thing I know. I know that sine of 1 over x has to be between negative 1 and 1. I do know that much because sine can be as large as 1, can't be less than negative 1. If I multiply everything by x squared, I get that x squared sine x is less than x squared, which is greater than or equal to negative x squared. Now, why are these two functions good? Well, let's see. What is the limit as x approaches 0 of negative x squared? Well, this one's continuous at 0, so just plug it in. That would be negative 0 squared, which is 0. I also know that the limit as x approaches 0 of x squared is also 0. So what I've just done is I've bounded my function between two different functions that have the same limit. By the squeeze theorem, what this tells us is that 0 is less than or equal to the limit as x approaches 0 of x squared sine of 1 over x, which is less than or equal to 0. Well, if something is less than or equal to 0 and greater than or equal to 0, this tells us that the limit as x approaches 0 of x squared sine x, or sine of 1 over x, is equal to 0. So again, I've bounded my function by something below and something above that had the same limit, which means that all three of them have the same limit. So that was also 0. So that's what the squeeze theorem says, is that if I can bound it below and above by something with the same limit, then the original limit is also that number. Okay, so that's the squeeze theorem. Let's try another example here. Let's say I want to look at the limit as h approaches 0 of sine of 4h over 4h. So the question is, what is this limit? Well, this looks very similar, so we're going to recall one identity. Remember that the limit as x approaches 0 or theta, whatever your variable is, of sine theta over theta equals 1. So remember that one. These two look the same, but they're not. How could I change my limit to look exactly like this other one, though? What happens to 4h as h goes to 0? So this is kind of an aside. The limit as h approaches 0 of 4h. What happens there? That's just 0. So what I can change this to is to be the limit as x approaches 0 of sine x over x. And we know that's 1 because of this property. So what I was able to do is kind of replace my variable. So instead of saying sine of 4h over 4h, since these two were the same, I could say this is the same as just sine x over x, where the x is going to 0 instead of h going to 0. So, using this, I was able to convert it to our standard form here, which is equal to 1. Okay, how about the limit as h approaches 0 of sine of 9h over h? Well, again, we're going to use this recall that I had up here, where sine of theta over theta is 1 for, should have been a theta, for theta going to 0. This isn't of the form sine of theta over theta because this needs to be a 9h. So what I can do here is change this to be a 9h, but once I put a 9h there, I've changed the problem. So I'm going to multiply by 9 to cancel out the 9 I just added on the bottom. So again, what I did is I changed it so that the 9h was also on the bottom, but I had to multiply by 9 to kind of cancel out what I just did. Can't change the problem. And now I can bring that 9 out front. So now I've changed it to 9 times the limit as h approaches 0 of sine of 9h over 9h. Well, we just did the previous problem where we had sine of something over the same thing was equal to 1. So this is just 9 times 1, which is 9. Because sine of 9h over 9h goes to 1, that was this property because these two thetas are the same. So I have 9 times the 1, which is 9. So again, what do we do on this one? We needed to have sine of 9h over 9h to use our property. These two thetas have to be the same. So I put a 9h on the bottom, but then I had to multiply by 9 to cancel out what I just did. So once I did that, I brought my 9 out front. That was the constant multiple. So I got 9 times 1, which was just 9. Okay, let's do another one here. How about the limit as theta goes to 0 of secant theta minus 1 over theta? Now, which one of our identities are we going to use here? Could we use the squeeze theorem? Could we use the sine or the cosine one? Well, this is in terms of secant, so I don't think we can do anything just yet. So I think what we should do is rewrite this inside function. What is secant theta? That's 1 over cosine theta over theta. Well, this hasn't really helped us out any. Let's see what happens if I combine these two on top. So if I combine the two fractions in the numerator, I'll get 1 over cosine theta minus cosine theta over cosine theta. So what I've done between these two steps is change my 1 into cosine theta over cosine theta so I can get a common denominator. So this is 1 minus cosine theta over cosine theta all over theta. Now, dividing by theta is the same as multiplying by 1 over theta. So this is 1 minus cosine theta over cosine theta times 1 over theta. Again, dividing by theta is the same as multiplying by 1 over theta. So this is 1 minus cosine theta over theta cosine theta. Okay, so what have I just done? I've rewritten my limit to be in terms of cosine. Okay, so let's see what happens here. My new problem is now that the limit as theta approaches 0 of secant theta minus 1 over theta is the limit as theta approaches 0 of 1 minus cosine theta over theta cosine theta. We've changed this to be in terms of sine and cosine. Here we just have cosine. Now what can we do? Well, let's recall one of our two trig identities that said the limit as theta goes to 0 of 1 minus cosine theta over theta equals 0. So we do know that. How can I pull out a 1 minus cosine theta over theta from this problem? What I could do is use my product rule, or my product property of limits. It says I can change this, to 0, to be 1 minus cosine theta over theta times the limit as theta goes to 0 of 1 over cosine theta. The reason I could do that is because this inside part could be broken up as a product. The product would be 1 minus cosine theta over theta times 1 over cosine theta. This first one, I know what that is. That's 0 by my property. Now what do I get over here? I get 1 divided by 1 when I plug in 0, so just 1, which gives me just a 0. Now, how did this actually help me? What I ended up doing, let's go through this one more time. I started with the limit as theta approaches 0, secant theta minus 1 over theta. Don't really know much about the properties of secant theta, so what I did was convert it into cosine. So I rearranged this fraction until I got it just in terms of cosine. So 1 minus cosine theta over theta cosine theta. Plug that back into my limit, so here was my new limit. Then I pulled out a 1 minus cosine theta over theta because we know what the limit as theta approaches 0 is of that. Pulled that out, evaluated the two limits separately using multiplication, got 0 times 1, which is just 0. So that's how you could use kind of rewriting it in terms of sine and cosine, and that's what we can get. Now let's do one more example. Let's look at the limit as x approaches 0 of cosine squared 3x over 1 plus x. Okay, so here's my limit. How am I going to evaluate this limit? Well, you might say I can't really use my 1 minus cosine theta over theta. That was this property. Can't really use that. It looks really weird. Doesn't look anything like it. Can't use my sine theta over theta because I'm not even involving sines here. So you might be saying, let's use the squeeze theorem. Sure, you can use the squeeze theorem. If you want to do that, squeeze it between the function 1 over 1 plus x and 1. You can squeeze it between that, but don't forget what we've already done with limits. Can I just plug in 0 into this function? You can. I'll get cosine squared of 0 over 1 plus 0. Well, cosine of 0 is 1, 1 squared is 1, 1 over 1 is just 1. So although we've developed these new techniques involving trig functions, you can always just go back, use your table in your calculator. You could do that, or you could say, well, this is continuous at 0, so I can just plug it in. So just because we have these new techniques involving the squeeze theorem and the two identities with sine and cosine, don't let that deter you from using what you've already done.